Hello all, today we are going to be solving radiometric dating problems, also known as half-life problems, because they're done in order to find out information regarding radioactive decay. There are a few purposes to half-life problems, including to find the amount of product created, to find the amount of original substance left, to find the number of half-lives, and to find out how much time has elapsed. The first type of problem is finding the amount of product created. In this case, we are creating nitrogen-14. If 250 grams of pure carbon-14 starts to decay, how much nitrogen-14 will be created in 28,500 years? So we are looking at 250 grams to start, and we're looking at how much nitrogen-14 in 28,500 years. For all of these problems, your first row is 0, 0, and 0 in the daughter and the time slots because no decay has started at this point. The carbon-14 is 250 grams, which we know from our problem. After one half-life, the 250 grams is divided by 2, and we get 125 grams. Then we do 250 subtract the 125, and we get 125 grams. When figuring out the daughter, you always start with whatever you started with in the problem and then subtract how much original is left. Then to find time, you take how much time is left is in one half-life, and you multiply it times however many half-lives you're at, which in this case is 1. So we have 5,700 years. You need to make sure that you are keeping with your units in your answer. You do not necessarily need to put them in the problem, but you definitely need them in your answer. After two half-lives, we have 125 grams divided by 2, which gives us 62.5 grams. Then we take our original 250, subtract the 62.5, and we get 187.5 grams. You are not expected to have all this math done in your head. You're absolutely welcome to use a calculator. Then we take the 5,700, and this time we're going to multiply it by 2 because that's the number of half-lives that we're at. That gives us 11,400 years. We're trying to get to 28,500. After our third half-life, we take 62.5, divide it by 2, and we get 31.25 grams. Then we take our original 250, subtract 31.25 grams, and get 218.75 grams. We take 5,700, multiply it times our number of half-lives, which is 3, and we get 17,100 years. We are still not at 28,500 years, so we go to 4. We take our 31.25, divide that by 2, and we're going to get 15.625 grams. Now, at this point, our decimals are getting a little bit crazy. So if you would like to round, you absolutely can. However, if you mess up rounding, you're going to mess up your problem. So I would be sure that you know your rounding rules before you try to round. So we get 234.375 grams after subtracting 250 minus 15.625. We take the 5,700, multiply that times 4, and we get 22,800 years. After 5 half-lives, we take our 15.625, divide that by 2, and we would get 7.8125 grams. Then we take our 250 from the original, and we subtract the 7.8125 grams. Again, you don't have to put them in your work. I automatically put them in my work just from years of doing these. It's not necessary. You only have to have them in your answer. You would get 242.1875 grams. And then we have 5,700 times 5, which would give us 28,500 years. Okay. After all is said and done, we are asking how much nitrogen-14 is created. So we have 242.1875 grams of N14 is created in 28,500 years. It's a good amount of nitrogen-14. Let's move that up a little bit so that everybody can see it. Next, we have the second type, which is finding the amount of original left. Again, first move, put 0 in your half-life, 0 in the daughter, 0 in the time. We have a radioactive material that has a half-life of 30 days. You begin with 4 grams of radioactive material. How much of the original is left unchanged after 90 days? 90 days, 1 half-life is 30 days. So we are starting with 4 grams. After 1 half-life, we have 4 divided by 2, which equals 2 grams. The daughter is going to be our original minus what we have in the first half-life, which is 2, to give us 2 grams. Our time is the amount in 1 half-life times the number of half-lives, which gives us 30 days. Then we have our second half-life. We have 2 divided by 2 equals 1 gram. Then we have 4 minus 1, which equals 3 grams. Then we have our original, which is 30, times the number of half-lives, which is 2, which gives us 60 days. Then we have 3 half-lives, which is going to be 1 divided by 2, which equals 0.5 grams. We have 4 minus 0.5, which equals 3.5 grams. And then we have 30 times 3, which is going to give us 90 days. Then we have to go back to our question. How much of the original is left unchanged after 90 days? 0.5 grams of the original is left after 90 days. You can continue to write out a sentence because that's the most clear, or you can just circle what your answer is, circle the block of what your answer is. That is up to you. The second type is finding the number of half-lives. In this case, we do not need to know the time that is in 1 half-life because we don't really care. We just care about the number of half-lives that it's going to be. So again, we're saying a rock sample contains 60 grams of a radioactive substance. How many half-lives have passed when there are only 7.5 grams of the same material remaining? So we start with 0 and 0. We are starting with 60 grams, and we want to know how many half-lives for 7.5 grams. So we have 60 grams. After 1 half-life, we have 60 divided by 2, which gives me 30 grams. Then we have the original amount, which is 60, minus the amount of the original, which is 30 grams, giving us 30 grams. After 2 half-lives, we have 30 divided by 2, which gives us 15 grams. We then take the 60, subtract the 15, and we get 45 grams. After 3 half-lives, we take the 15, divide it by 2, give us 7.5 grams. Then we take the 60, subtract the 7.5, and that gives us 52.5 grams. Now our question was, how many half-lives have passed when there are only 7.5 of the same material remaining? So this 7.5 is right here. So 3 half-lives have passed when 7.5 grams is remaining. Okay? Again, you can just circle your answer, but it's also helpful to write it out so that you're sure that you're answering the question fully. The final type is finding out how much time has elapsed. Now, before we start this problem, I would like to teach you an abbreviation. If I have billion years ago, I can abbreviate that with BYA. That is what we are going to use for the time here, because it says an 80-gram potassium sample has decayed to contain 5 grams of potassium 40. What is the age of this rock? Assume a half-life of 1.3 years, billion years. Make sure you keep that billion in there. It is very important. So we have 80 grams. We want to know how much time is going to elapse when it gets to 5. Okay? So we have a half-life of 0. We have our original is 80 grams. Our daughter is 0. Our time is 0. After 1 half-life, the 80 has divided by 2 to give us 40 grams. Our daughter is 80 minus the amount of original to give us also 40 grams. Our time is 1.3 times 1, which gives us 1.3 billion years ago. You have no reason to put the billion in your work because it's not necessary. Let's make sure that decimal point's a little bit darker. The half-life is 2. Then we have 40 divided by 2 equals 20 grams. We take the 80, subtract the 20, that gives us 60 grams. Then we take 1.3, multiply that times 2, that gives us 2.6 billion years ago. So we're still moving because we still have 20 of that original left. So we have 20 divided by 2, which gives us 10 grams. Then we have 80 minus 10 to give us 70 grams. We have 1.3 times 3. That gives us 3.9 billion years ago. So now we're on our 4th half-life. We have 10 divided by 2, which equals 5 grams. We have 80 minus 5, which gives us 75 grams. And then we have 1.3 times 4 gives us 5.2 billion years ago. So again, when we go back to that question, we have an 80-gram sample that has decayed to contain 5 grams of the potassium 40. So make sure you're looking at your headings. What is the age of this rock? Based on our calculations, the rock is 5.2 billion years old when it has decayed to 5 grams. Now, biggest mistake students make is they do all this work right, and then when they write their answer, they forget to put billion years. So please don't let that happen to you. Thanks very much, and good luck.